Hi there, this is the RPS project. I'm Richard, and today I'm going to have a quick look at the Bandpass filter. This is the passive RC Bandpass filter. Very simple device, very easy to get to grips with. It is effectively a low pass and a high pass filter put together. Now, if anybody's seen the last couple of videos I've done, which was basically one on a low pass filter and one on the high pass filter, I've just put them together to make my Bandpass filter. I've actually got it here on the whiteboard so you can see what I'm talking about. And basically what I've got is my high pass and then a low pass filter. Because it's the same as before with the low pass and high pass, the equation for working out what the cutoff frequency is going to be is exactly the same, hasn't changed. Frequency equals 1 over 2 pi RC. Very simple for both of them. Now, I was wondering which one comes first, the high pass filter, low pass filter, or low pass filter, high pass filter. Now, I've drawn a quick chart at the bottom here just to try and explain that, how I got to grips with working that out. Frequency against amplitude. If I put the high pass filter in first, what it does is and set it with a low cutoff frequency, it gets rid of all the stuff that I don't want that's below that frequency. So I don't get it, and then it comes up and then it's in the frequency bandwidth that I want it. And then the low pass filter with a high frequency cutoff point will then attenuate anything above that and just allow through the frequencies below it. So we end up with this frequency coming through between here and here is the main frequency. So there'll be a midpoint where it's at its strongest. I'm getting most of that signal through. There are some calculations to work out this stuff, but I'm not worried about that. I just want to see if I put a high pass filter then a low pass filter that I will get attenuation below it, attenuation above it, and I'll just get some frequency at the midpoint coming through at its strongest. Very simple. Now, I did wonder if changing these round and having a low pass and then a high pass would have any difference, but well, I'll have a look at it and see what happens if I get a chance and see if that has any effect. But the main thing is this, high pass and low pass. Now, the values I'm using is a 1k resistor on both of them. Now, the high pass filter, I'm using a 220 nanofarad capacitor, which supposedly should give me a cutoff frequency of 723 Hz, and the low pass with a 47 nanofarad should give me a cutoff frequency of 3.38 kilohertz. So sort of 720 Hz up to about 3.4 kilohertz. So that's my bandwidth. So I suppose in the middle is about 1.6, 1.5 kilohertz. So I might start at the midpoint and see where we go from there. Anyway, I have got this set up on the breadboard behind me, so let's get and have a look at it. Okay, so here we have the Bandpass filter set up on the breadboard here. Got a resistor here and then a capacitor, so that's, well, capacitor, sorry, then resistor, so that's my high pass filter, and then it goes through this resistor, and I've got another capacitor there, and that's my, on this side, my low pass filter. So comes in high pass, low pass, and that's my output. That's my input, and everything else is the same, really. So let me just pan up to the scope, because that's where all the action's going to be. I can zoom in a bit more. Yeah, there we go. That's it. So turn on the channels. Now, when I looked at this, I set this up so I should supposedly have a high pass cutoff of 723 Hz. So that's going to get rid of all my low stuff, and then I'm going to have the bandwidth that I want up to the cutoff points of 3.38 kilohertz, and then I'll have my low pass filters attenuating everything else. So, well, I don't know, I suppose midpoint 2 kilohertz or 1.5, 1.6. I'm going to set it to 1.5 kilohertz I'm going to start it there and see what I've got. And there you go. I've got a filter that's giving me an output that is, I suppose, probably again it's going to be about -3 dB because we've got a bandpass filter. We've got no phase shift, so we're in pretty much the middle of that frequency range, but we're always going to be slightly less than the input frequency. And then as I get lower below my cutoff point, the high pass filter is going to attenuate this, and as I get higher and get a higher frequency, my low pass filter is then going to attenuate this signal above its cutoff point. So if I now take this frequency down to about, well, it's about 700 Hertz now, so we're around about that high pass filter's frequency cutoff point where it's going to start to really attenuate. Let me just adjust this scope. 400, 300. Need to really get some signals in there. We're now at 2 milliseconds per division on the time, and as you can see, it really is, and I'm at 100 Hertz now, and it's just really demolished that low frequency. But then if I turn the frequency up, we are now at the 1.5, and again I'm just going to adjust this scope so we can see it a bit better, and that's about the midpoint. Supposedly if I take it up to about 3.3, 3.4 is going to be the cutoff point. And as you can see, the other thing about it is as we move away from the center point, we get the phase shift that we'd expect with a low pass and a high pass filter. So we're edging towards the low pass filter's cutoff point, so we've shifted forward, shifted positive, is it? Phase shift from our center point, and as I turn that up, as you can see, the frequency is now being attenuated on the output all the way up to, let's crank it up to sort of 10 kilohertz, and you can see that that's really sort of attenuated it. So let's bring that all the way back down, back to the, what we're on, that was a 3.4, that's its low pass filter cutoff point. And if I crank it all the way back down, and I'm just down to about 1.5, and you can see there's no real phase shift in that. Again, now I'm going to change this so I get a lot more on there, because when I crank it down to the high pass cutoff point, which is about 700 Hertz, as you can see, the phase shift is now shifted the other way to the minus phase shift. It's going that way in the phase shift because it's the high pass filter cutoff point that's now affecting the signal. As you can see, if we go down 1 Hertz, yeah, it's almost killed it off. So yeah, that seems to work really well, really. I mean, it does what I'm expecting it to do. So I'm just going to turn this back up to the 1.5, and let's do a frequency sweep. Now I've set this up to be 100 Hertz up to 5 kilohertz. So let's turn that on and see what it does. We're starting at 1.5. It's going to rise and then fall. So as it rises, past the 2 kilohertz, 3 kilohertz, that signal, output signal, is getting smaller, and then it's going to get to 5 kilohertz, and it looks a bit crammed on there, but I want to be able to see this low end. But that signal is getting smaller. I know we can't see the phase shift with this much on the screen, but it is getting smaller. And then obviously it's going to get bigger as we come down the frequencies, past the 2, past the 3, past the 2 kilohertz, and we're nearly at 1.5. There we go, past the midpoint. We're now at 1 kilohertz, 700 hertz, and it very quickly tails off as we get down to the lower frequencies. and as you can see, and then it starts coming back up. So I'm just going to try and stop this on the midpoint, about 1.5 kilohertz. 3, 4, 5, there we go, it's about it. And yeah, that's to me a good demonstration that a high pass then low pass filter is a bandpass filter, a passive RC. Low frequencies, if you set the high pass filter to have its frequency cut-off point lower than the low pass filter, all the low stuff gets cut off. At the midpoint there's no phase shift, and then as it goes up there's more phase shift towards the low pass, and then all the high stuff gets cut out. To me, I think that works just fine. Now, as a little extra, I've now swapped my, and I can't see it here, but I've swapped my filters around. I've now got a low pass filter and then a high pass filter, and I don't know if you can see this, but actually this signal here, the output signal, is nowhere near as big as the output signal was when I had it the other way, high pass, low pass. As I say, now I've got a low pass, high pass filter set up, and it's not as big. This is a lot smaller. I mean, let's just do a quick measure, see if I can get this. Channel 1, the amplitude here is on channel 1 is, yeah, it's about that 500 millivolts, 496 thereabouts. Yeah, I'll allow it. I'll take my measurement from the output signal. It's 224, so it's less than half. So that's not minus 3 dB. That's a lot more of a signal loss, all because I've changed my filters round. So it does look like that is actually quite important. So what I'm going to do is I'm just going to run the frequency sweep just to see how it looks and see if there's what the changes are. So now by rights it should be attenuating it once I get past the 3.4 kilohertz, and there is some phase shift, but look, it's not attenuating it. It's not making that output signal smaller, and it should be. We're nearly at 5 kilohertz. And then as it comes down the frequency, you can see the phase shift is working, but it's not done nothing for the signal amplitude. It's still the same. Come past near to that midpoint again, about 1.5 kilohertz. And as it gets smaller, we should see it being attenuated, but it's not getting smaller really. I expect when we get right down to the bottom level, some attenuation there between 100 and 300 hertz, but it shouldn't be doing that, should it? It should be stop that about there. It should be attenuating this properly, but it's not. So putting the filters in the right order does seem to be important. You seem to need to have the high pass filter and then the low pass filter, otherwise this thing doesn't work properly. So there you go, that's the band pass filter with a passive RC, low pass and high pass filter put together. Very simple. I suppose what you could do with that is you could try and narrow that bandwidth. You know, if you used specific capacitors, you worked out what the midpoint was going to be, and then you used the right value of, well, capacitors and resistors, so you can get the frequency cutoff points as close to that center point as you want, until you get quite a narrow bandwidth. You can have it quite wide, you know, and have a really wide range of frequencies going through, especially if, let's say, at speakers and you want a certain range, and you go, well, I want quite a lot of range in there, let's say from 1 kilohertz all the way up to 10 kilohertz. You can do that, you can make it so it's going to have that, but on the other hand you can have it really narrow, so you just want like equivalent to 1 kilohertz range bandwidth going through that filter. I suppose you could do it. I mean, I suppose as you get more technical about it, you need better filters, more specific filters than just a basic passive RC filter. But I mean, you could set it up so you're just having the bass frequencies come through, or the mid or the treble frequencies, and set the filter up that way. Very simple. On the other hand, you could use it, I suppose, for RF devices where you want a really specific narrow bandwidth of frequencies coming through. Mind you, RF circuits are somewhat more complicated than just a basic RC passive filter, way above what I know about at the moment as far as doing filtering goes. But I'm sure there's obviously going to be reasons where you want to see that specific bandwidth and know that maybe you're tuned into it or something like that, or you just want that particular frequency to come through. So I imagine there's quite a lot of applications for things like this. So there you go and have a play and have a look. And if you didn't like this video, you know what to do. If you did, give me a thumbs up, subscribe, and all comments are welcome. Press the bell icon. See you next time.